A prime number is a number greater than 1 whose only divisors are 1 in itself. 13 is prime because nothing between 2 and 12 divides it. 10 is not prime because 2 and 5 divide it. We want a quick way to decide this for any number without testing every single value below it. The clever bit is the same pairing idea as divisors. If a number has a factor, that factor comes with a partner, and one of the two must be no larger than the square root. So we only need to test divisors up to the square root of n. If any of them divides n, it is not prime. If none do, then only 1 and itself divide it, so it is prime. We also rule out numbers below 2 right away. First, we reject anything below 2 since 0, 1, and negatives are not prime. Then we test divisors starting at 2, but only while I times I is at most n. The moment 1 divides n cleanly, we return false. If the loop finishes with no divisor found, the number is prime, so we return true. Let's build it live and test primes and non-primes together. Numbers below 2 are never prime, so reject them immediately. Test divisors up to the square root, and bail out the moment 1 divides n. Try the next candidate, and if none divides n, the number is prime. Now let's test it and hit run. Seven and 13 have no smaller factor, so they are prime and come out true. 10 is divisible by 2, and 1 is below 2, so both are false. The flow is short. Reject numbers below 2. Then test divisors up to the square root. If any divides n, answer false. If the loop ends clean, answer true. Because a factor and its partner straddle the square root, we only test up to root n, giving order root n time. We keep just a counter, so the space is constant. This is dramatically faster than checking every number below n. Remember to handle small numbers first, because 0, 1, and negatives are not prime. Keep the loop bound at the square root for speed. And note that 2 is prime, the only even one, and this loop reports it correctly since 2 times 2 already passes 2.